efficiency. What is efficiency? Efficiency, simply put, it describes the energy that a certain system can extract and make useful. So I'll write this here. It describes the energy that a certain system can extract and make useful. And this obviously needs to come from an energy source. So whatever the energy source is, so for example, let's say it's hydroelectric. Or let's say a power plant. Any system such as this, such as these two examples here, uses energy from fuel. And of course, this is always going to have some sort of efficiency. So any system such as these, so any system that uses energy from fuel has an efficiency. Let's get another example over here with coal. Coal has an efficiency from what I believe around 32%, and something a little bit better would be like natural gas or nat gas, and I think that's around 40%-ish. Let's look at this coal here, this 32%. What does that mean? This means that for every 100 joules of heat, only 32 joules becomes useful. So in our case, we want it to become electricity, for example. So only 32 joules becomes electricity. Because obviously you have your denominator here as 100, so 32 over that as a numerator, because this is what you're getting out of it, okay? Obviously we would want theoretically 100 joules, but it's never going to be 100% efficient. So let's say we only get 32, right? You just multiply by 100%, right? So it's only 32% efficient. So only 32% of it actually becomes the electricity that we want. The rest just gets dissipated as heat and is lost. Now, it's important that we understand that efficiency is not the same as effectiveness. Efficiency does not equal effectiveness. Now, what is the difference? Well, this efficiency is pretty much what I was just talking about, right? Right up here, okay? It's the energy that a certain system can extract and make useful. How much energy are we able to get? However, effectiveness is not really that. It's just simply making use of the energy to become the right goal. So maybe I'll add this over here. It's simply the use of energy to get to the right goal. All right, an example of this would be like a car, okay? So a car goes from A to B. This is technically effective because the goal of the car using the fuel is to drop off people from point A to point B. However, the efficiency is a little bit different. Depends on the car utilizing the fuel in a way where not a lot of it gets dissipated as waste, but goes specifically into the actual transportation, getting from point A to point B without losing so much dissipation. But the car itself, whether it's a very good car or a bad car, both are going to be effective because they both accomplish the goal of getting this person from point A to point B. One car may not do it very well, but either way, regardless of which one is better, both get the goal done. So both are technically effective, but one car may be a lot more efficient than the other one. There's also a formula that you need to know. So our energy output is also going to be known as our Q total. So the total amount of heat gained or lost, and it's all going to be summed up as a total, all put together. So it depends on the mediums in question. So if we have our Q, the amount of heat absorbed for medium 1, but we have another medium in question that also absorbed or released amount of heat, let's say that's medium 2, because we have these two mediums working in conjunction with each other, that is containing the system, we actually have to add these both up. Even if there's medium 3, medium 4, you have to add them all up for our total amount of energy output. The total amount that actually came out from the system that we were able to measure. So this here is pretty much what we were able to measure. Okay, not theoretical, but it's actually the amount that got measured. Then we also have our energy input. What is our energy input? Our energy input is also known as the delta H. So our delta H, it comes from, remember that formula, delta H is equal to N times delta HR. Right? This here was the molar enthalpy, and then this here was the amount of mole, because this over here is our theoretical amount, right? This was our theoretical amount of energy content of the hydrocarbon stored. Being released. And you're going to be getting this value from likely a data chart or a data table, and that specific hydrocarbon, if it releases a certain amount, that total amount should be going straight into our Q total, right, into our medium 1 and medium 2. But however, not all of it gets absorbed into our mediums 1 and medium 2. Maybe it goes out into the environment outside of the actual calorimeter, for example. Or it just doesn't get captured and we just weren't able to read it. But theoretically, this amount should be going straight into here. We just have to make sure that we quantify how much actually went in and then determine the efficiency. How efficient was it to go from here to here? So our delta H here is going to be the theoretical amount of energy that got released. So we just have to do our little calculation here. That's going to give us our delta H, the amount of energy released. So then this here becomes our input. This is technically what we'll want. So I'm just going to put here, this is theoretical. This is what we should be getting. Okay, so if we had to put our formula, our energy input here, our input, this is theoretically what we're supposed to be getting. It's like on a test, you're supposed to be getting 100%. So on a test, this would be like, out of 100, right? Out of 100 marks, for example. But how much do we actually get, right? Of course, we all want 100, but that's kind of unrealistic. So if it's unrealistic, that's actually going to be our output. So this is going to be our energy output. Okay, so this is our energy output, what we're supposed to be getting out of 100 marks. You're supposed to also multiply this all by 100% in order to get a certain percentage, because whenever we look at efficiency, it's based on percentages. So we're just going to get this divided by this multiplied by 100% is the actual amount that we're supposed to get. So again, this here is our optimal amount to obtain. Okay, optimal to attain. And then our energy output here is how much actually went into the surrounding. Okay, amount into the surrounding. Let's give it a try with some few questions. All right, let's do this question over here. We see our ethanol is going to be the one that's being burned, is being combusted, but we have two mediums. Our first medium here as our surrounding is our glass beaker, and our other medium is going to be the water. So I'm just going to separate this both. So I'm just going to have our glass beaker first here, glass beaker, and I'm going to have water over here. Maybe I'll give some more space just in case. Now to start putting them together, we have our glass beaker first, so we'll do our Q is equal to MCT form. Let's see if we are missing any variables. So we have our Q is equal to MCT, and our M here is going to be the mass of the glass beaker, and that we're given it, so we have a 386 grams, and we are going to obviously multiply it by our specific heat capacity. Does it tell us? Yes, it does. It tells us that it's at 0.880. So 0.880 0.80 joules per gram degrees Celsius. And then we have to multiply it by our T. Do we have our T value? I mean, we started here at 15.5 degrees, and then at the very end, it went up to 48.7. So I'm just going to do a quick calculation here. 48.7 subtracted by 15.5, I end up getting 33.2. So it's going to be 33.2 degrees Celsius. And then I'm just going to multiply all of these together. I end up getting 11,277.38. Okay, this is the amount in joules, because of course these grams cancels out because technically this is over 1, so you have fractions, so diagonally, if they're the same, right, these units will then cancel out. Same thing here, this diagonally cancels out with that one, so then our Celsius goes away, so we're just left with our joules. Now we're just going to do the same thing for water. Okay, so water, again, does it say anything about its mass? Well, yes, so it tells us that there's 125 grams of water, so I'm just going to write that here. And then I need to multiply it by our certain specific heat capacity. Does it tell us? No, but if we look, I mean, you should have already memorized it right now, right? But if you can, as you can see in our chart here on the side, you see our liquid water here is at 4.19, right? See that 4.19? So always keep note of that. It should have already been memorized, but just in case you didn't, right, it's 4.19 joules per gram degrees Celsius. And then we're going to get our temperature here, because here as well 15.5 is where it started, and then it became 48.7, so it's the same change in temperature. So then I'm just gonna multiply them all together. This cancels out, this cancels out. See what you get. I end up getting this many joules. So all we're going to do is now starting to add these together, because remember the formula, right? You're supposed to get your Q total, right? How do you get your Q total? You're supposed to get the Q's from both mediums added together. So I'm just going to sum them up together here, and then what do we end up getting? We end up getting 28,665.88 joules. Right? So this is the amount of heat that got so the heat gained or released. And obviously in this case it was gained, because the system, the ethanol here, was exothermic, right? It was burned as fuel. So all that heat got blown out, okay? And where does it go? It's going to go into its surroundings, right? Whatever's around it. So obviously the glass is around it, and obviously the water is around it. So those are going to be taking that heat in. So it took in that much heat, okay? So it took in that much energy, 28,665.88 joules. Well, the question is also asking now for the efficiency of the transfer of heat to the beaker and the water. So this is how much it came in, right? Obviously, this may not be the total value that we actually wanted. We have to figure out how much was optimal to attain, right? The energy input. This here was the output. How much was actually inputted, right? That theoretical amount that we should have gotten. Well, we're going to have to figure it out, but they do tell us a hint here that the enthalpy of combustion of ethanol is that much, 1,366.8 kilojoules per mole. Now, when we look at this per mole, right, this means this is our delta HR. Our delta HR is always going to be represented in the amount per mole. Now we need to find our delta H, because our delta H here is going to be telling us how much energy was able to be released, and that released energy went into our Q total, the amount of heat absorbed. Well, how do we figure out what our delta H is going to be? Our delta H is going to be our amount of moles multiplied by our delta HR. In this case, we're not using delta HR because they tell us that the delta HR is specifically going to be combustion. So we could actually just change our delta HR to be delta H com. It doesn't matter, okay? R or combustion, they're going to mean the same thing in terms of our concept. Well, we have to get our delta H is equal to the amount of moles of the ethanol. Do we know how many moles of ethanol we have? No, it doesn't tell us that in the question. But we can multiply by our delta H com, which is going to be what they're giving us, right? Or 1,366. I'm going to put a negative symbol here. And again, this is going to be in per mole. However, I don't want it in moles, right? Because we want eventually our delta H, and our delta H is going to be a kilojoules value or joules value. This is what we want, because then we can compare this joules value, solely the joules, with the amount of joules that got absorbed. So how much of this, our delta H, got absorbed into our Q? We got to compare them. But again, we can't get rid of the moles unless we know what the moles is here, because once we have moles here, right, technically that's over 1, so anything diagonally, if they're the same unit, they'll cancel out. So then I'm just going to be left off with my kilojoules. So how do we figure out our moles over here? We have C2 H5OH, and we know that its mass, as indicated right over here, is 1.24 grams up there, so 1.24 grams. So we can easily find the amount of moles by just doing 1.24 grams multiplying by some fraction. We can just put grams on the bottom, that way they can cancel out, then we're just left with our moles on the top, okay? That's exactly what our plan is going to be. So how many grams per mole of it, our molar mass for C2H5OH exists? Well, we got 2 carbons here, and then we got 6 hydrogens, and we got 1 oxygen, so we're just going to add them all up from our periodic table. We get 46.08 grams per mole. So then this and this cancels out, so then we just get our 1.24 divided by our 46.08, so I end up getting 0.02, okay, 0.026909. Okay, I can even add a 7 over there. Okay, so this is the amount of moles that we have. So I'm just going to put this back into that equation. So I'm going to get my delta H is equal to our 0.0269097 moles. I'm going to multiply it by our value over here. That way, sideways here on the side, diagonally they cancel out, and then I end up getting a value of negative 36.78. And this is in kilojoules. Now I can't do anything in kilojoules. I need to make it into joules. So I'm just going to change this into joules. So I get negative 36, okay? Move this 3 decimal places, 1, 2, 3, okay? So I get 780 joules. So this is the amount of energy that got released, right? 36,780 joules. And it's supposed to be that amount into our Q, right, our surroundings. But we only ended up getting 28,665. So we're just going to do our percent efficiency formula. So we got 28,665.88 joules divided by our value here, only 36,000. Again, I don't have to put a negative sign there because we know that this is exothermic. It got released and put into there, so we're just arbitrarily seeing the difference. So we got 36,780 joules. I'm just going to multiply by 100%. And then what answer do we end up getting? End up getting 78%. Let's try this question here. As you can see, a flame calorimeter determines the heat content, the energy release per gram of the fuel burned of the wood. Which one is going to be our 2 mediums? We see our first medium is our aluminum can. That's going to be our first medium. And then our second medium is going to be our water. Okay? Well, let's first figure out the aluminum can. It has a mass of this much, so I'm just going to use my Q is with MCT formula. My M, right, because our first medium is going to absorb a certain amount of heat, right, from the fuel burned, is going to go into it. So this aluminum has a mass of 180.51 grams. We need to multiply by a specific heat capacity. Do we have a specific heat capacity of aluminum? Well, if you just look over here on the side, you see how it's 0.897, right? So I'm just going to highlight in red over here, right? We have 0.897 joules per gram degrees Celsius. I'm going to have to multiply by our change in temperature. Well, we started at 15.6 and then we ended up with 20.7. So we're just going to do a quick little calculation here. And they're getting we end up getting 5.1 degrees Celsius. So I'm just going to do my little calculation here, and I end up getting 825.78. And again, this cancels out, this cancels out, this cancels out, this cancels out, so I end up getting this many joules. Now I'm going to do the same thing for the water. So our MCT, what do we get for our mass? We get 1 kilogram, but I'm just going to change it to grams, so we end up getting 1,000 grams. I'm going to change my specific heat capacity. I know it's not written there, but you should already know by now that our water, okay, as written over there, is going to be our 4.19 joules. Okay, so 4.19 joules per gram degrees Celsius, and then multiplied by the total amount of temperature change, okay, which is going to be the same value, our 5.1 degrees Celsius. I'm just going to cancel these out, so I end up just getting a value of 21,369 joules. Now I'm just going to get my Q totals, so by adding these up, I'm going to get the total value of 22,194.78 joules. Now, is this what we want? Well, let's look at question A. Calculate the energy output that is absorbed. Well, it seems like that is the answer, right? It got absorbed by this medium, and it got absorbed by this medium. So we're just adding them up. We get the sum. Now, that is A. Now we got to answer B. An estimate of the recoverable heat content for the wood is 6.5 kilojoules per gram. So let's write that out. The thing is, we don't have 1 gram, right, of the wood that is being burned. We end up getting 5.5 grams of wood being burned, right? So this is just 1 gram, so I don't want that. I want 5.5 grams that is being burned. So then that way I can just cancel out my grams here. So then how much is the total amount of energy then, rather than just 1 gram? I just have to multiply them. I'm getting 35.75, so 35.75 kilojoules. And again, I don't want to use it in kilojoules because I want to measure this delta H that we got, right? The total amount of energy from the system that got burned. Where did this energy go? It went into our aluminum can and the water. Okay, so again, if we want to compare these two values here, right, we have to make sure that this is in the same unit. So rather than kilojoules, I'm going to change it into joules. So I'm just going to add another 0 there. So I'm just going to get 35,750, okay, into joules. And I'm just going to compare these two together. And in fact, that's actually what we're going to be doing on letter C, right? Letter C is saying determine the efficiency of the system. So how are we going to determine the efficiency? Well, we have to do our percent efficiency. And then we have to get our input. Our input is the theoretical amount that we're supposed to be getting, right? So as you can see, this is what we're supposed to be getting. So we're going to put this in our input in the denominator. And then what we actually got, that we actually measured, was 22,194.78 joules. Okay. And then I just have to multiply by 100%. So what is our total value now? After you do this calculation, I'm getting 62%. What mass of pentane would have to be burned in an open system to heat this much grams of hot chocolate? Well, as you can see, we have our specific heat capacity here, so obviously we got to do some sort of Q is equal to mCT formula. Let's give it a try. Well, how many mass do we have? Well, we have this much mass. We have 250, as you can see, 250 grams of the hot chocolate. And then we have our specific heat capacity of this value of 3.59 joules per gram degrees Celsius. And then it changed with this difference in temperature. So we had 39.8 minus 20, and we're getting 19.8 degrees Celsius. So then my joules here, my degrees here, it cancels out. So what do I end up getting in total? I end up getting 17,770.5 joules. Now, this is the amount of joules that got released. Well, what is the question asking? What mass of the pentane would have to be burned if the energy conversion is only 45% efficient? Well, this here is what we got. How much are we actually supposed to be getting? So this means we have to use our percent efficiency formula. And again, remember, it is the energy of the output on the top and the energy of the input on the bottom. Which one is going to be our output? Well, this here, our Q is equal to mCT. Remember, Q is the amount of heat gained or lost, right? So if we're gaining it over here, because obviously a pentane is being burned, so it's going to release energy, so it's going to gain something for our Q, right? Our Q is what we actually end up gaining. So it's the amount of heat that got released and it got gained by whatever our medium is. In this case, our medium was the hot chocolate. So our hot chocolate here is going to be getting a certain amount of energy, and in this case it's going to be this much. So I'm just going to substitute this with our hot chocolate value, and then my efficiency here is going to stay as 45% because that's what is written. So I'm going to put 45% is equal to our energy output. Okay, so our energy output is going to be 17,770.5 joules. And then our input, we actually have no idea, so I'm just going to keep it as our question mark. So how do we figure out what our mass is going to be? Well, in order to figure out our mass, we first have to figure out our moles. Do we know what the amount of moles is going to be for the pentane? Well, we can use our delta H is equal to our moles times our delta HR formula. Well, we got to figure out what our moles is. So what is our delta HR and what is our delta H? Once we figure out those values, we can isolate for our moles. Where our delta HR over here is going to be our pentane. So we could actually find it here. Our delta HR is actually going to end up becoming delta H comb. So rather than delta HR, again, they're the same. So the delta H comb, the specific combustion one over here is going to be delta H comb. And what value do we have? We can see here on the very, very side, for our pentane, it's negative 3,509. Okay, negative 3,509. So that means our value here is going to be times negative 3,509 kilojoules, okay, per mole. Okay, so obviously we want to keep the amount of moles here. That means we have to get this delta H value and figure it out. Well, delta H is going to be the amount of energy that is being released and put into our Q. Now, ideally, we would want that to be a perfect ratio, right? Whatever amount came out here from the system goes into the surrounding of the hot chocolate, but we can't add that particularly well together because it's only 45% efficient. But we've actually already done that over here. We know that it's only 45% efficient, and we're trying to find our E input. Our E input is literally that. It's our delta H, the amount of energy that is being released from the system. So if I find my question mark over here, this means that this is our delta H. So what I'm going to do is figure out what our 0.45 is. So our 0.45 multiplied by our question mark is equal to 17,770.5 joules. So then we're just going to get our value here as 39,490 joules. So I'm going to put this value where our delta H is. So I'm just going to put that into here. So we end up getting 39,490 joules. And again, this is the amount of energy released, so I could keep my negative symbol over there. And then it's equal to our moles. So how do we end up finishing up this example? Well, this is multiplying by this amount. I want to isolate my n alone, so I got to get rid of this. So what's the opposite of times this? It's going to be divide this. I'm just going to divide this by the value over here. And then if I do it on the right side, I need to do it on the left side, so I'm going to do it here. So then what do I end up getting? Well, first, this here is our joules, so I got to change that into kilojoules. So first, let's cancel these out. So our moles is going to be left over here. I'm going to change this joules into kilojoules. So it's going to be negative 39.490 kilojoules. So that this one can stay in kilojoules per mole. Okay, so then this cancels out, this cancels out. So I end up just getting this value divided by this value, 0.1125 moles. So what value of this mole is going to become our mass? So I'm just going to change this into our mass. So again, we have our 0.01125 moles. And I need to multiply by a certain fraction, so I have moles on the bottom. So I'm going to put grams on the top. That way I can keep my grams isolated and left. So I just want to get rid of my moles. These moles are going to cancel out. Well, for our pentane, we look at our C5H12. You just go on the periodic table, right, and then find our molar mass. So this here is our molar mass. I'm just going to get this value and multiply by this value. That should give us our final answer. I end up getting 0.81 grams. And this here is our green question of the day. We got 2 questions, right? A and B. Please pause the video, give this a try, and then I'm going to be giving you the answers shortly. This is the answer.